Swayam Prabha. Digital India. Educated India.
Hello, welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture we initiated a discussion on the one-way classification, and we had utilized the principle of least squares to do the same analysis to obtain the same statistics that we had earlier obtained using the likelihood ratio test. So, now you should be confident that either you try to use the likelihood ratio test or the principle of least square, you are going to get the same outcome. And after that, next question is, in one-way classification you are trying to study the effect of only one factor. This means you are assuming that your outcome is going to be affected only by one factor, but there can always be many situations in real life where more than one factors are going to affect the outcome. For example, you know that whenever we are trying to make a clinical experiment and we are trying to see the effect of different doses of the medicine on the patients, then the doses of the medicines are going to affect the patient, but don't you think the age of the patient also affects it? For example, you have seen on the medicine that it is written that for young children, those who are between say 0 to 5 years, they have to take quarter spoon of the say medicine. Those who are between say 5 to 12 years, they have to take half a spoon of the medicine, or those who are more than 12, they have to take 1 teaspoon of the medicine. What are these things? There is a dose and there is an dosage factor, and both are going to affect the effectiveness of this medicine. In case if a adult takes only a quarter spoon of the medicine, that is not going to be possibly effective. So, now we are going to consider here the setup of two-way classification, where we assume that there are two factors which are going to affect the outcome. Now, before I move further, I must tell you that in the earlier lecture also, whatever we have done, that was to give you an idea that what will happen in the higher order interaction, and it is very important that you try to do all this algebra, whatever I am trying to show you here on the slides and by writing yourself. The one-way classification that we did earlier, that is now going to lay the foundation of the learning in the two-way classification, and whatever we are going to learn in the two-way classification, that is going to lay the foundation for the higher order classification, which we are not doing here, but that you have to understand. So, once you understand one-way classification, two-way classification, I am more than confident that there should not be any problem in understanding higher order analysis of variance. So, from that point of view, you try to understand this lecture. And definitely, as I said, in this two-way classification, I am going to use the details, fundamentals and algebra, whatever I explained you in the earlier lecture in more detail here directly. So, it is very important for you that you should be clear about the concepts, expressions, everything what we have covered in the last lecture. So, okay, by this assumption that you know all these things, we begin our this lecture. Okay, so in this lecture we are going to talk about the two-way classification without interactions in the experimental design models. So, first we try to understand that how are the things going to happen, and based on that we will try to prepare the background. Suppose the outcome of a response variable that depends upon two factors, say A and B. So, we have two factors, factor A and factor B. For example, suppose there are I varieties of mangoes which are grown on say I different plots of the same size in each of the j different locations, right. And suppose all plots are given the same treatment like equal amount of water, fertilizer, etc. And then definitely we know that whenever there is a crop, the crop depends on the variety of the crop as well as the location where it is grown. For example, if you try to grow coconut in the southern part of India or in the eastern part of India, you can grow them very easily, and but if you come to a place like IIT Kanpur, here if you want to have coconuts, possibly it is very difficult to grow the tree, because the climate here is not favorable for the growth of the coconut. So, this is the type of experiment or situation that I am going to consider here. So, now I have here two factors in this experiment, which we are assuming that they are going to affect the yield of mangoes. Well, there can be more factor, but here we are not growing the mangoes, but we are trying to understand the two-way analysis of variance. That is what you have to keep in mind. Okay, so, now I denote the location of the plots as factor A and the variety of the mangoes as factor B. Such an experiment is called as two-factor experiment, right. Now, why this is called as two-factor? Because there are two factors. For example, in this case, different locations correspond to the different levels of A, that is factor A, and the different varieties of the mangoes, they are corresponding to different levels of factor B. For example, if you try to take say 3 possible varieties of the mangoes, right, then there will be the different levels of the factor B. And if you try to take the different location of the plots in the same region, they are going to indicate the different levels of the factor A, right. And remember one thing, we are at this moment trying to collect the observation on the basis of per plot. That means, we are getting only one observation per plot, right. Well, after that we are going to consider the other case also. So, I will try to make it here clear that here now we are going to consider only one plot per observation. And now you see, when you are trying to see the effect of two factors A and B in the outcome from the same plot, there can also be the combined effect of both the factor. So, the combined effect of the two factors A and B is called the interaction effect of A and B, because in the earlier case we had only one factor. So, one factor cannot create any interaction, but once there are two factors, there can be effect of factor A, factor B, as well as their interaction effect, right. So, now once we try to consider the option of interaction effect, then we have here two options. Either we can have only one observations in a plot or one observation per plot, or there can be more than one observations per plot. Well, now definitely if there is only one observation from a plot, then there cannot be any interaction. You cannot study the interaction effect among the observations, and we simply assume it to be 0. Right. There is only one observation. So, how can you study the interaction effect? But if there are more than one observations per plot, then the interaction effect among the observations can be considered. So, now on the other hand, I will say the same thing in a different way, that if you think that the two factors are going to be affecting the performance of each other, then you try to collect more than one observation per plot. But if you think that no, the interaction effect is going to be nearly 0, then you can just collect one observation per plot. So, it depends on you that what type of experiment you are trying to handle and what is the objective of the experiment. So, now we can consider here two possible cases, one observations from a plot in which the interaction effect is 0, and more than one observation or plot in which the interaction effect is present. So, now we are going to consider here the one observation per plot case. So, that means we are going to consider here the two-way classification model without interaction, and obviously the model is our fixed effect model, as we said earlier that unless and until we are trying to say that the model is random effect model, the model will remain as the fixed effect model. No confusion from this point of view. So, now you can see here we have here only one observation per plot, and there are two factors which are going to affect it. So, definitely you have here the observations here y, and now the question is how many subscripts it has. So, there are two factors here. So, I try to take here two factors I and j, and all the observations are going to be indicated by here y I j, right. So, now in case if I assume that this y I j be the value of the response of observation from the ith level of the first factor say A and the jth level of the second factor say B, and we are assuming that y I j's are independently distributed. Well, because you have to keep in mind that finally you are going to use the setup of linear model. So, you have to frame this model keeping in mind the application of the required statistics, right. So, now I can assume that here y I j's are coming from the normal population with mean mu I j and variance sigma square, and here this subscript small I is going from here 1 to capital I, and subscript small j is going from 1 to capital J. You see, I have chosen here this capital I and capital J and the limits of small I and small j of the subscript. So, that it is easier for us to remember that what are the limits of I and j. So, I means the limits are 1 to capital I, and for j the limits are 1 to capital J. So, that is easy to remember. One thing I would like to make it here clear that here I am trying to write down that they are trying to follow the normal distribution. So, well, normal distribution is not going to be required in the beginning when we are trying to estimate the parameters of the model, but that is required when we are trying to construct the test of hypothesis. But now you understand these basic fundamentals. So, I can write it down from the beginning itself. So, now I am going to do the same thing what I did in the case of one way ANOVA when we reparameterize the model. So, now you can see here the expected value of y j here is mu I j. Now, you have to understand what I am trying to do here. Now, you have here two factors here A, B and their interaction, which is indicated by say A B. Now, you have to divide this mu I j in the form of linear contrast such that the contrasts are corresponding to the factor A, factor B and factor A B. So, now you have to move intelligently, you have to think intelligently, and then you have to adjust your model in the exactly same way as we did in the case of one way classification. So, the knowledge what you have gained in the one way classification, that is going to be used here, and after that I will be 100% confident that if you have to extend this model for the three way analysis of variance, there should not be any problem. So, from this point of view, let us try to do it. So, now if you try to see here that I am trying to add here say a term like mu I naught, I am trying to add and subtract here a term like mu naught j, and I am trying to add here the term like mu naught naught, because I know that factor A for I, factor B for j and factor A B for say something like mu I j, which is already there. So, now if you try to see I am trying to adjust it. How I am trying to adjust it? Mu I j is now written here as say mu double naught plus mu I naught minus mu double naught. So, you can see here this is indicating the presence of here I. So, this can possibly indicate the effect of the ith factor, right. And similarly, if you try to see here I am writing mu naught j minus mu double naught. So, this is involving here a subscript j. So, this is going to represent the effect of the jth factor, and then I am trying to write down here mu I j minus mu I naught minus mu naught j plus mu double naught. So, this is involving here the both subscripts like I and j here you can see here. So, this is going to indicate the joint effect of the factors a and b. So, I am trying to now indicate here say here this mu double naught as here mu, this here quantity here mu I naught minus mu the double naught as here say alpha I, and for this mu naught j minus mu double naught it is here beta j like here like this, and this terminology the last term this is indicated for gamma I j which is written here. And now, if you try to see here what is really happening, this mu I naught this is getting cancelled by here like this quantity, mu naught here j this is getting here cancelled by here this quantity, and mu double naught this is going to be cancelled by here like this one, this one, this one, and here this one. So, now finally, you have only here mu I j which is written here as here mu I j. So, you can see here I have just adjusted the mu I j in a way such that every treatment can be presented in the form of an contrast. So, here we have an elementary contrast as well as a contrast here in terms of gamma I j. So, you can see here that this alpha I mu I naught minus mu double naught, and in the beta j mu naught j minus mu double naught they are your elementary contrast, and for this gamma I j this is also here a contrast, and you can see here that summation I goes from 1 to capital I alpha I is here 0, and summation j goes from 1 to capital J beta j this is also here 0. Right. So, now you can see here you have reparameterized the model expected value of here this y I j to here mu plus alpha I plus beta j plus gamma I j. Right. So, now this alpha I is trying to indicate the effect of the ith level of the factor A, or you can see here this is defined here as you can see here mu I naught minus mu double naught like here this one. So, this is trying to measure the excess of the mean of ith level of A over the general mean. So, you can see here mu I naught minus mu double naught, and similarly here beta j is the effect of jth level of B, which is like here mu naught j minus mu double naught. So, this is trying to indicate the excess of mean of the jth level of B over the general mean mu double naught, and gamma I j here is the interaction effect of ith level of A and jth level of B. But here in this case we are collecting only one observations per cell. So, we are assuming that gamma I j is equal to here 0. So, our model will simply become here y I j is equal to mu plus alpha I plus beta j plus epsilon I j. But you have to be a little bit careful that in this case we are assuming this gamma I j to be 0, but in the next case when we are trying to consider more than one observation in a cell, then we will try to consider the gamma I j in the model, right. So, now we also assume here that for the model expected value of y I j is equal to mu I j is a full rank model, right. So, that your mu I j or all the linear parametric functions of mu I j are estimable. Now, we will assume it now, means we will not try to discuss or raise the same issue again and again, because we know that estimability is an issue. So, we will try to represent the parameters in the form of a linear contrast. So, there is no question, but it does not mean that if I am not talking of those issues over here, they are not there, they are there, but now we are simply trying to use the same philosophy of one way classification for both the effects for factor A and factor B. So, these effects are going to be there, and we are going to handle them in exactly same way as we did in the case of one way classification. So, the total number of observation in this case will be I into j, and these observations are going to be arranged in a two way classified I cross j table, where the rows correspond to the different levels of factor A and the columns correspond to the different levels of factor B. So, how it will look like? Just like here this, the observations on y the general mean effects and the I levels of factor A and j levels of factor B, they are indicated here like this. So, you can see here that this is here y response, mu here is general mean effect, alpha 1, alpha 2, alpha I, they are the I levels of factor A, and beta 1, beta 2, beta j, they are the j levels of factor j. So, now if you try to see here, when you are trying to take the alpha 1 level of factor A and say beta 1 level of factor B, then you have here an observation y 1 1. Right, and you try to repeat these observations for different combinations of alpha and beta levels. So, and then in case if you try to keep the alpha 1 level here fixed, like here this one, and you try to change the beta levels here like this. In the first case you are using beta 1, second case you are using beta 2 up to here, and then you are trying to use here the beta j. So, these values are going to be represented here like this. And similarly, you can do for here all the levels of alpha and beta. So, finally, you will see here there are here say all the levels of here alpha I also, corresponding to which we have considered all the combinations of beta j. So, now if you try to see, this is here a part which is your here the design matrix X, and this is here the part which is your here y, and this is your here the part here for general mean effect, and your parameter vector is going to be here like this one, which is containing the parameters mu, alpha 1, alpha 2, alpha I, and beta 1, beta 2, beta j. So, in this table I have tried to give you the model setup. Okay. So, now in case if the design matrix is of full rank, there is no problem, but if the design matrix is of not the full rank, then the model can be reparameterized, right. That now you know, there is no further discussion on this issue. Now, you know both the things, and in case the model is not a full rank, then we can write any model in the format of expected value of y I j is equal to mu plus alpha I plus beta j, and you can impose suitable conditions on alpha I and beta j. So, now that we have understood, now when you are trying to consider the two-way classification, you have here two factors. One are represented by alpha 1, alpha 2, alpha I, they are the I levels of factor say A, factor 1, and the second factor say here B has k levels. So, that effect is indicated by beta 1, beta 2, beta j. So, now we have here two null hypotheses in which we are interested, one related to alpha and say another related to beta. So, the null hypothesis for alpha is indicated by here H naught alpha, which is alpha 1 equal to alpha 2 equal to alpha I is equal to 0, and the null hypothesis for beta is indicated by H naught beta, beta 1 equal to beta 2 equal to beta j is equal to 0. Right, this is exactly on the same line as we did in the case of one-way classification in the last lecture. And similarly, now you can have here the alternative hypothesis. So, the alternative hypothesis corresponding to alpha is at least one of the alpha I is different from others, and for this H naught beta, the corresponding alternative hypothesis is H 1 beta, that at least one beta j is different from other effects, right. So, now you have these null and alternative hypothesis. Do not you think that is it looking like as if there are two types of one-way model, one related to alpha and one related to beta, right. So, now if you try to think of doing the analysis of variance the way you have done earlier, that you tried to find out the sum of its squares under H naught. So, now you have to do the same thing under H naught alpha and say under H naught beta separately. Means earlier you had found the sum of its square due to treatment, but in this case you have to find two types of sum of squares, that is sum of square due to treatment A and sum of square due to treatment B, and the total sum of square that will remain only as one total sum of squares, and the sum of square due to error that will remain as only one, that will be obtained after fitting the model. So, now if you try to understand this approach, now there is no issue. Now, we come to employ the least square principle for estimating all the parameters mu, alpha I and beta j. Or equivalently, now I can say whether you employ the least square or the maximum likelihood estimation, both are going to give you the same result. Now, you have understood all the things. Yeah, only the estimator of sigma square is going to be changed, but now you understand the entire philosophy. So, now what we have to do? The first step is this, that we have to assume that alpha I and beta j are not equal to 0, and then we have to find out the estimates of mu alpha I and beta j, and then we will try to assume that first H naught alpha is true, and then we will try to find out the estimate of the parameter, and then we will try to see that what happens under when H naught beta is equal to is true, and then we try to find out the estimate of the parameter. So, these are the three steps. So, first we try to consider the step number 1. We are trying to write down here the sum of square due to random errors, which is double summation I goes from 1 to I, j goes from 1 to capital J, y I j minus mu minus alpha I minus beta j whole square. So, this is simply your here double summation epsilon square I j, and we try to minimize this error sum of square such that so that you can obtain the estimates of mu alpha I and beta j. So, we try to differentiate here E, the error sum of square with respect to mu, with respect to alpha I, with respect to beta j, and you can see here that these three normal equations are here obtained like this one. Simple differentiation. Now, you know that you can solve these equations to get the unique estimates only after imposing the condition that summation alpha I is equal to 0 and summation beta j is equal to 0. So, if you try to impose these conditions over here in the first equation, you can see here this is double summation y I j minus say n times here mu minus summation alpha I something minus summation beta j something. So, summation alpha I and beta j are here 0. So, this will give you here mu hat is equal to n times say here g upon here n, which is equal to here y bar double dot. And similarly, if you try to solve these two equations here, you simply try to substitute here mu equal to mu hat here, and then try to use this condition summation alpha I and summation beta j is equal to 0, you obtain here the estimates of alpha I and beta j as like this. So, now means I have done this algebra in the last lecture in detail. So, I would leave up to you that you simply try to solve these simple equations, and then you can see that you can obtain here that mu hat is equal to here 1 upon I j. So, n here is the same as here I into j, because n is the total number of observation that you took earlier as n1 plus n2 plus np. So, now this is simply here say I into j, then double summation I j, which is coming here say g upon capital I j. So, g here is the grand total of all the observations that you have obtained by taking all combinations of the factors of levels of factor A and factor B. And similarly, if you try to solve here this equation, this partial derivative of E with respect to alpha I, and try to use those conditions, then you can obtain here alpha I hat here, let us say 1 upon j summation j goes from 1 to j y I j minus y double naught, and this quantity which you are using here summation over j y I j, this is indicated by here T I. So, this T I is the treatment total due to the I hat effect or the sum of all the observation receiving the ith treatment. That is the same thing which you learned in the case of one-way classification. So, now you can see here, if you are not clear about the one-way classification, it will become difficult for you to understand, because even now I am not explaining that much which I did in the case of one-way classification, because I assume that you have learned those things. So, now you can see here, this I can write down here, say T I upon j minus y bar double naught. And now, if you try to see what is here this quantity T I upon j, this you have indicated earlier as y bar I naught, right. And if not clear, then you can directly look over this expression. Do not you think that this is how you have defined earlier this quantity y bar I naught, and then this is here y bar naught naught. So, before I go further, can you observe here one thing, that you have obtained here alpha I hat here as a y bar I naught minus y bar naught naught. Can you compare it with the same alpha I hat that you have obtained in the case of one-way classification? The forms are the same, and this is a very interesting observation which I am going to use further, but here I would like to have your attention, so that when I try to ask you to recall from the past, then your mind should come to this point. Okay. Now, I try to take the other equation, that partial derivative of E with respect to beta j, and I try to solve it. I get here the least square estimate or the maximum likely estimate of beta j as beta hat j, which is equal to here 1 upon I summation I goes from 1 to capital I y I j minus y bar double naught. Now, if you try to see here this quantity here summation over I y I j, this I am trying to denote here by here b j, right, and b j is indicating here the block total due to the jth effect or sum of the all the observations in the jth block. Well, what is here the block, that is not clear to us at this moment, but in case if you try to see that you are trying to arrange these observations in a, say here, sort of table where you have a here I number of rows and columns. So, you can assume that, for example, these are some particular blocks and some particular rows, but definitely this concept of block and rows will get more clear when we are trying to use the randomized block design that we are going to discuss after a couple of lectures, right. But then I thought that I must inform you here, so that once you have done the randomized block design, after that once you are trying to revise these lectures, you can understand them very easily. So, okay. So, in case if you have any confusion, you simply take it as here that this is the sum of all the observations in the jth block, right. So, now if you try to see here, you try to look at the structure of this 1 upon I summation over I y I j. This is nothing but your, in your symbolic notation, this is y bar naught j. And if you try to see this y bar naught j is simply your here b j upon I. So, now this beta hat j becomes here y bar naught j minus y bar double naught, right. And then once you have obtained the alpha I hat, you have obtained the beta hat j, that means you have obtained alpha 1 hat, alpha 2 hat up to alpha I hat, and beta 1 hat, beta 2 hat up to beta j hat, right. So, now you have estimated all the parameters, but if you try to write down here the expression of beta hat j, you can see here that how it looks like. You can see here one thing, both this alpha I and beta j, they are going to be measured from their mean of all the observation y double naught. And if you try to see the structure which I explained you earlier in the case of one way, because I will try to extend it to a two way also. You can see here in the one way we had talked about it, that here is an I in alpha hat I, and here is y bar I naught. And similarly for the beta hat j, you have here j in the subscript of beta hat j, and then you are trying to take it here y bar naught j. So, can you see a sort of relationship between the I and j of the estimator and the different types of mean? This is what you have to keep in mind, that I am trying to write down here y bar, and when I want to have here alpha hat I try to write down here y bar I, and when I am trying to write down here the estimate for beta hat j, I am simply write down here y bar j. And yeah, means because this is based on 2 subscript, so other 2 subscript I try to indicate by here not. This is what you have to just keep in mind. Well, it is not a trick, that is how we are getting it mathematically, so there should not be any confusion. But still this is the pattern which you are getting, and that is going to be helpful for us. So, that is why I am trying to have your attention here. Okay, now we try to find out the sum of squares due to error, exactly in the same way as we did in the case of one way analysis of variance. So, can you recall how we had found that error? We had simply considered the sum of square due to error, say the double summation epsilon square I j, and then we had written this epsilon I j in terms of the model, and then we have replaced the parameters by their estimated values. So, this SSE is going to be the minimum value of the sum of square due to errors, which is obtained by replacing the parameters by their estimated value. So, this becomes a double summation I and j y I j minus mu hat minus alpha I hat minus beta j hat whole square. And if you try to simply substitute these values and try to take a paper and a pen and try to square it, you will get here a very simple expression. Just try to substitute the values which we have obtained for mu hat alpha I hat beta j hat, and just try to simplify it. You will get here like this, and if you try to square it and then just simplify it, you will get here this expression double summation y I j minus y bar naught whole square minus j times summation over I y bar I naught minus y bar double naught whole square minus I into summation over j y bar naught j minus y bar naught whole square. Now, this is the same approach that we opted in the case of one way analysis of variance. So, I will ask you that you please try to just open this square and simply try to simplify it. You will get such an expression. Surely, if I try to do this algebra over here, you will get completely bored. Right. So, now, this is what we have obtained here, the sum of square due to error. And now, about the degrees of freedom, we know that we are trying to use here the Fischer Cochrane theorem. So, this degrees of freedom can be obtained by the degrees of freedom of this factor minus the degrees of freedom of this factor minus the degrees of freedom of this factor. So, the degrees of freedom of the factor number 1 is I j minus 1, the degrees of freedom of the second factor is here I minus 1, and the degrees of freedom of the third factor are j minus 1. So, if you try to simplify it, you will get here I minus 1 into j minus 1. So, this SSE is going to have a distribution with I minus 1 and j minus 1 degrees of freedom, and now you know which distribution, that will be chi-square, you know it. So, no, okay, after this I try to do the same thing what we did in the case of one way analysis of variance, that we try to put one of the factor to 0, and we try to do the same analysis when H naught alpha is true. That means, all alpha 1, alpha 2, alpha I are going to assume the value 0. So, in this case your model will become simply here y I j is equal to mu plus 0 plus beta j plus epsilon I j. So, now do not you think that this becomes just like a one way model? That is the same model that you did earlier, but now the only thing is here that in this case your alpha i's are replaced by beta j. So, now do you think that I should do the entire algebra once again? I am sure that if you are in the class you will say no. So, I will follow your advice, and I will simply try to follow the same approach that we followed in the case of one way analysis of variance, and I will try to minimize the error sum of squares, which is double summation over I and j y j I j minus mu minus beta j whole square. and then we try to differentiate even with respect to mu, with respect to beta j, put them equal to 0, obtain the normal equations and solve them, and after that if you try to do it, you will get here mu hat is equal to y bar double naught, and beta hat j will come out to be y bar naught j minus y bar double naught. So, now you can see, if I try to do the same algebra and try to show you the same thing, I am once again confident that you will get completely bored, and I am sure now that you have understood that how are you going to obtain this result. On the other hand, if you have not understood, then it is the point of trouble and you need to look into your earlier lectures, then you try to proceed further. But in case if you try to observe here, this expression of beta hat j which you have obtained after substituting all alpha i's to be 0, this is the same as earlier, right. If you try to see here, this is the same effect which you have obtained here. Here I am trying to make a circle. Now, you can see that if that why this statistical assumptions are needed. Right. Okay. Now, I can find out here the once again the sum of squares due to error when h naught alpha is true. So, we call it as a sum of squares due to h naught alpha. So, we understand that okay, under this case h naught alpha is true. So, this is going to be the minimum value of the same sum of square due to error which is here even, which is obtained after substituting the values of mu and beta j in this expression SAC. So, you simply try to substitute it here, and you can see here this mu, alpha I, beta j, they have been obtained in this entire analysis such that the sum of a square is going to be minimum. So, obviously, when you are trying to substitute these values in this expression for the sum of a square due to error, that is obviously going to give you the minimum value of that sum of a square due to error. So, now if you try to simply just substitute the values of mu hat, substitute the value of beta j hat and try to expand it, it will come out to be j times summation over I y bar I naught minus y bar double naught whole square plus double summation here y I j minus y bar I naught minus y bar naught j plus y bar double naught whole square. So, now this first term is simply your here sum of squares due to factor A, and this factor here, the second factor is simply your here a sum of squares, and the logic here is the same. If you try to see the difference between E1 minus E, so in this E1 you are trying to put alpha I equal to 0 and only beta j are there, whereas in the case of here E, your alpha I and beta j both are not equal to 0. So, in case if you try to find out the difference between them, this will come out to be as this is the error due to the factor A, right, because only factor A has been put as say on and then off in the two situations. So, that is why this term is called here as say sum of square due to factor A, and that can be obtained just by subtracting it from the earliest sum of squares exactly in the same way as we did earlier. So, this is called as sum of square due to deviation from h naught alpha. Yeah, because when h naught alpha is true, then this effect is simply 0, right. So, when you are trying to deviate from the null hypothesis h naught alpha, then it is coming into picture. And you will see that there is another name for the sum of a square, which is sum of a square due to rows or sum of a square due to the factor A, right. That will be more helpful when we are trying to do with the designs of experiments. So, now I can write down here that sum of a square due to A is going to be defined by j into summation I goes from 1 to capital I y bar I naught minus y bar double naught whole square. And if you try to simply open it, this will come out to be j times summation over I y square I naught minus I j into y bar double naught square, and this carries here I j minus I minus 1 into j minus 1 degrees of freedom, which if you simplify this will come out to be here I minus 1 degrees of freedom. And even if you want to see it directly here, you can see here that this component here, this is based on say I terms, but there is a one constraint, that summation over I y I naught bar minus y bar naught naught is equal to 0. So, under this constraint one of the degrees of freedom is getting lost. So, this one is coming over here. So, you can see here that this degrees of freedom has got different types of interpretation, different types of meaning, and different types of ways in which you can look upon them. So, this depends on you how you want to do it. Now, we try to do the same exercise when H naught beta is true. Right. So, now under this case, when you are trying to say that H naught beta is true, that means all beta 1, beta 2, beta j, they are equal to 0, and your model becomes here y I j is equal to mu plus alpha I plus 0 plus epsilon I j. So, now once again, don't you feel that this has become just like a one way analysis of variance model? Yes. And now you have to just follow the same step that we used earlier in the case of one way analysis of variance, and we simply try to minimize the sum of a square due to random errors, which is double summation y I j minus mu minus alpha I whole square. Then we try to differentiate it with respect to mu, with respect to alpha I, and we try to obtain the normal equation, and we try to solve them. As simple as that. So, now you can see whatever you have learnt earlier, that is simply going to be repeated again and again. So, if you try to solve this equation, that partial derivative of E2 with respect to mu is equal to 0, this will give you mu hat is equal to y bar naught naught. That is, this is the arithmetic mean of all the observations. And if you try to solve the second equation, that the partial derivative of E2 with respect to alpha I, then it will give you here the estimate of alpha I here as say alpha I hat is equal to y bar I naught minus y bar double naught. And you can see here that I have taken here this symbol here E2. So, we have here E, we have here E1, and we have here E2. So, E has both alpha I and beta j. E1 has here say alpha I equal to 0 and beta j not equal to 0, and E2 here is alpha A is not equal to 0 and beta j is equal to 0, and in the first case both are not 0, that is obvious. So, that is why when we are trying to compare this E1 with E and this E2 with E, we are trying to get the effect of factors A and B in terms of their sum of squares. Now, before I try to go further, can you really see this expression? Can you recall the expression that you had obtained for this alpha I hat in the case of one way analysis of variance? Don't you think that both are going to be the same expression? Well, the values are going to be different, the sum of squares are going to be different. I am not saying that they are the same thing, but their structure of alpha I hat, that is the same, that you have to keep in mind. Right. And similarly, now I can obtain the other sum of squares under this E2. So, what we have to do? We simply have to write down here double summation y I j minus mu minus alpha I whole square, and then we have to replace mu by mu hat and alpha I by alpha I hat, and you simply try to substitute those values over here and simply try to solve it. And you will see here that we are getting here an expression there I times summation over j y bar naught j minus y bar naught naught whole square plus double summation y I j minus y bar I naught minus y bar naught j plus y bar double naught whole square. Well, you can ask me here why I am trying to partition it into two parts. Well, you see, my objective is very clear. I want to see the effect of factors A and factor B. So, I am trying to express this factor as a function of SSE. And with that objective, I am trying to add and subtract here terms like here y bar double naught and y bar naught j. right. So, if you try to see here, if you try to obtain from the second step to third step, you have to add and subtract here the terms y bar naught naught, and then you have to subtract here the terms here, add and subtract y bar naught j. And after that, if you try to solve it, you will get, and the cross product term will become 0. So, this first term here is the sum of square due to the factor b, and second term you can verify this is the simply your error sum of squares. So, now this variation here is partitioned into two parts, sum of square due to factor b and sum of square due to random error. So, now you have here E, which is having both alpha I and beta j which are not equal to 0, and then now here you have E2 which is having here say alpha I equal to 0, but beta j is not equal to 0 in general. So, the difference in the sum of squares which are indicated by E and E2, that we can consider as if they are trying to indicate the effect of the factor b, and that is why we say here that the sum of square due to the factor b is indicated by this factor I into summation j goes from 1 to capital J y bar dot j minus y bar double naught whole square, which can be expanded as a I into summation over j y bar square naught j minus I into j y bar square double naught. Right. Okay. So, this quantity is also called as sum of square due to deviation from H naught beta, because that is coming when H naught beta is not getting accepted. Well, all the betas are not equal to 0. And this is also called as the sum of square due to columns or the sum of square due to the factor b, right. And in the same way as you had obtained earlier the degrees of freedom, you can obtain the degrees of freedom due to SSB by ij minus I minus 1 into j minus 1, which are the degrees of freedom of your SSE, and this will come out to be here j minus 1. And actually you can also once again obtain this degrees of freedom directly from the expression of SSB, because this is based on say here j values you can see here, but there is a one constraint, that summation y bar naught j minus y bar naught naught is equal to here 0, right. So, this constraint is decreasing the degrees of freedom by here 1. So, this becomes here j minus 1, right. So, now you have obtained all the SSA and SSB, and now we try to obtain here the total sum of squares, and I will try to show you that how this can be partitioned into these components. Very simple job. So, now as per the definition of total sum of squares, this is defined as double summation over I and j y I j minus y bar double naught whole square. That is, if you try to see, this is the one of the denominator of the variance, that is simply you are simply trying to see the variance type of variability around the mean of all the observations. Now, if you simply try to add and subtract here, see here y bar I naught, y bar naught j, right, and then try to adjust these terms by here y bar naught naught, right, then you can write down here the same quantity here as a y bar I naught minus y bar double naught, y bar naught j minus y bar double naught, plus y I j minus y bar I naught minus y bar naught j plus y bar double naught whole square. And if you try to just open it, there will be 3 terms which are here, and and all other cross product term will become 0, right. So, cross product terms, all terms will become 0. Very simple exercise, very simple algebra, and you will get here the first term here is like this, second term here is like this, and third term here is like this. And if you try to identify what are these things, the first term here is j summation over I y bar I naught minus y bar double naught whole square, which is your here SSA. The second term here is I times summation over j y bar naught j minus y bar double naught whole square, which is your here sum of square due to b. And the third term here is double summation y I j minus y bar I naught minus y bar naught j plus y bar double naught whole square. This is your here SSE. So, you can see here you have partitioned the TSS into 3 component, SSA, SSB and SSE, and the degrees of freedom of this TSS is going to be simply the addition of the degrees of freedom carried by SSA, SSB and SSE, which is coming out to be here I j minus 1, right. Now, using the same theorem 7 and 9 that we did in the case of earlier lecture, in case of one-way analysis of variance, we can very easily prove that SSA, SSB and SSC, they are mutually orthogonal, and they have got the degrees of freedom as we have given here. Now, if you wish, you can assume that Yij's are independently distributed and following a normal distribution. Well, this is the place from where we will need it, right. Earlier, although we had assumed it in the beginning, but now here we have a need. So, I am just repeating it here. And now, using the theorem 7 and 9 that we did earlier, we can write down here that SSA upon sigma square follows a chi-square distribution with I minus 1 degrees of freedom. SSB upon sigma square will follow a chi-square distribution with j minus 1 degrees of freedom, and SSC upon sigma square will follow a chi-square distribution with I minus 1 into j minus 1 degrees of freedom, and all these chi-square distributions are actually central chi-square distributions. So, now you have 3 independent chi-square random variables which are following a central chi-square distribution. So, now you can create the test statistics for H naught alpha and H naught beta exactly in the same way as you did in the case of one-way classification. So, you can see here, if you try to use here the SSA upon sigma square divided by I minus 1, SSC upon divided by their degrees of freedom, this will come out to be simply here the I minus 1 into j minus 1 divided by I minus 1 into SSA upon SSC, which is simply your here actually mean square due to A divided by mean square due to error, and this is going to follow a F distribution, or rather a central F distribution with I minus 1 and I minus 1 into j minus 1 degrees of freedom under H naught alpha. Right, and if you try to recall, this is the same statistic that we had obtained under the likelihood ratio test for H naught alpha. Right, that is similar to your one-way classification. So, now the decision rule is straightforward, that reject H naught alpha if f1 is greater than the tabulated value, which is obtained by f1 minus alpha and I minus 1 and I minus 1 into j minus 1 degrees of freedom. Right. If H naught alpha is not true, then under H1 alpha, this f1 will follow a non-central F distribution. The degrees of freedom will remain the same, but the non-centrality parameter will be added here, which is given by delta is equal to j times summation alpha I square upon sigma square. And now, the same thing you can also do for the null hypothesis H naught beta, that you try to write down the sum of square due to B divided by sigma square divided by their degrees of freedom j minus 1, and then try to divide it by the sum of square due to error SSE divided by sigma square divided by the degrees of freedom, and try to take the ratio. So, both are going to follow the chi-square distribution, both are independent. So, now this will translate to I minus 1 into j minus 1 SSB upon SSE, and then this is simply the ratio of mean square due to the factor B and mean squared error. That will follow a central F distribution with j minus 1 and I minus 1 into j minus 1 degrees of freedom under H naught beta. So, now this is again the same thing what you did in the case of one-way analysis of variance, and so the decision rule comes out to be here H naught beta, that if f2 is greater than f under these degrees of freedom. And the same test statistics you had obtained under the case of likelihood ratio test statistics. So, all this computation can once again be represented in the framework of an analysis of variance table. So, the source of variation here are factor A, factor B and error, and then obviously the total. The degrees of freedom are here I minus 1, j minus 1 and then I minus 1 into j minus 1, and for total this is I j minus 1. The sum of squares are SSA, SSB, SSE, which is obtained by subtraction, and the total sum of square is TSS. Then you obtain MSA, MSB and MSE, and then you try to obtain here F1 and F2. As simple as that, nothing more to discuss here now. And you can find the expected value of MSA, MSB and MSE. I am not doing here the proof like here this. So, you can see here one beautiful part, that if all alpha i's are 0, then this term is going to be 0 under expected value of MSA, and if all beta j's are 0, then this term is going to be 0 under expected value of MSB, and expected value of MSE comes out to be sigma square. So, we have to keep in mind that MSE is going to give us an unbiased estimator of the sigma square. Now, in case if the any of the null hypothesis H naught alpha or say H naught beta is not accepted, then we try to use the multiple comparison test either on alpha i's or beta j's, and we try to divide the entire population into different groups such that the effects of the alpha I and beta j's which are similar, they are clubbed in the same group. Right. Okay, so now we come to an end to this lecture. So, I would request you that you please try to find and derive all those expressions with your own hand. Unless and until you do it, you will not gain confidence. I am promising you the algebra is very simple, but it is going to take some time only. So, you try to practice it, and I will see you in the next lecture with more details. Till then, goodbye.